Thanks, John, for the introduction. So, as you can see, it's a very complicated topic for today's presentation. Basically, the key words in the title is, first is trigger responsive, second is a drug conjugate for encapsulates. So I will first give some brief introductions about the background of my research and show you some sort of like very surprise discovery I found during my studies and some downstream studies for it. So basically, we are particularly interested in polymeric encapsulates for cancer therapy. In recent years, people have discovered that nanoparticles for drug delivery will be much better than simply small molecule drug delivery, considering the long blood circulation of nanoparticles as well as the EPR effect for tumor targeting. However, when we try to fabricate polymer drug encapsulates, there are a lot of issues we need to deal with. The first issue comes with what kind of carrier we choose to encapsulate the drugs. So people have screened for a lot of different polymers to prepare all these nanostructures, as well as with different class of nanostructures as we have shown here, including micelles, polymorphism, etc. But for all these systems, there are a lot of issues for them. For example, the structure turned out to be heterogeneous considering the polymer structures, and the polymer drug interaction turned out to be quite subtle for either for prediction or either for experimentally to reproduce them. Two very important issues in all these systems is that first is the control release. I will show you in the next slides. The second issue is the low drug loading efficiency and low drug loading for the carriers and drug. So why we care about trigger responsive therapeutics? As we can imagine for nanoencapsulate, for example, micelle encapsulated drugs, a very important issue, serious issue in it is that the drug will leak out of the micelles, no matter what kind of condition it is, as long as it is in water. So we can imagine when we deliver the drugs inside of our bodies, the drug will leak throughout the bloodstream when it travels around. Before it arrives at the tumor tissues, maybe more than 50% of drugs already leaks out. And we know that a lot of these cancer drugs, they have a very severe side effect. So we don't want all these drugs to leak out of the carriers before it reaches a certain site. So here comes the idea of trigger responsive therapeutics. So we sort of like to have a release kinetics shown from these figures here. So we try to have a trigger responsive strategies for it. Before any trigger treatment, the prodrug is sort of very stable within the particles, but after a certain treatment, we can sort of control either the release kinetics of the drugs and try to further stabilize all these released drugs, either in the certain cell organelle or the cell compartment. Another issue for all these encapsulates is drug loading. As we can imagine, if we have a 20% drug loaded micelles or nanoparticles, 80% of it is just a carrier polymers. Of course, we will worry about safety issues of all these polymers. And another issue is loading efficiency, which means that when we try to prepare 10 grams of drugs mixed with polymers, maybe only 5 grams of the drug encapsulated, and the other 5 grams just lost during the process, which certainly is not good for us. So people have developed a variety of strategies to try to make high-loading nanoparticles for drug delivery, but limited success have been achieved. For example, like for certain type of very special polymer structures, they can capture certain drug structures for it and reach around 40% drug loading. As I want to tell you first, like for general, all these drug encapsulate systems, the drug loading is less than 20% in general, and loading efficiency is less than 50%. And some other strategies include drug assembly or like made a very complicated synthesis for prodrug and made it assemble, which is more beyond our knowledge. It's really even harder to predict all these behaviors. So here's the outline of my discovery, and I'll show you next for my presentation. So first, I'll show you a structure of my high-loading so-called cathode conjugate, and some detailed mechanistic studies to show you how it is formed through nanoprecipitation method, and some sort of studies, including fluorescence studies, to show you the solid state of all these nanoparticles, and show you the trigger responsive property of my nanoparticles, and some anti-cancer efficacy studies follow up. So here's where the story begins. So here's the drug structure of the cathode. The reason why we are interested in this drug is because first, it's a very potent anti-cancer drug, and it is a very special DNA topoisomerase inhibitor. But the issue with this drug is that the water solubility of this drug is extremely bad. The water solubility is less than 10 microgram per ml, which means that it's really hard to deliver it in vivo anywhere else. it will certainly aggregate and precipitate out of water when we try to dissolve it in either PBS buffer or some other aqueous solutions. And why we're interested in this drug for trigger-responsive delivery is that cathosicin is very special. As we can see from structure, it has only one active hydroxy groups in the structures, which can be very easy for us to modify it. And besides, the substructure I circled here is very important for its activity interaction with the DNA and topoisomerase. Once we cap this hydroxy group here, the anti-cancer activity of this cathosicin is completely lost. So here is a very sort of weird structure we designed for another project actually. As we can see from structure, we kept the hydroxy group of the cathosicin through a certain carbonate bond linkage. So through that, without any trigger treatment, this prodrug should not be toxic to cancer cells. However, as we can imagine from these chemical structures, the drug is even more hydrophobic than cathosicin itself. The water solubility is even worse. So how can we deal with it and how can we deliver it? Actually, JJ asked me to just try to do a nanoprecipitation to make it a particle and try to see what will happen. So I will just briefly introduce. I think most of you guys have to go through the Summer Institute for nanoprecipitation to prepare nanoparticles. So basically the idea is we dissolve our drugs with a co-block polymer, which is PAC-PLA, which is exactly the same we use for this year's Summer Institute I made. And we dissolve it in DMF and add it dropwise into water solution with magnetic bar to mix it, and we form nanoparticles. What is really surprised me and my advisor is that we found that the system turned out to be very special. In general, for cathosicin encapsulate, the loading rarely exceeds 10%, and loading efficiency is always less than 10% as well, which means that the total drug loading will be around 1%, which will be sort of like ideal for a normal cathosicin encapsulates. That's also the reason why cathosicin is rarely used for clinical trials, because it's really hard to fabricate to prepare the nanoparticles. So here comes my formulation result that we can see here. When we tune the ratio of my drug versus the polymer I use is PAC-PLA, we can see that the nanoparticle size doesn't change much, while the loading efficiency is almost quantitative with a drug loading even more than 50%, indicating that majority of the nanoparticles is composed of my drug instead of the polymer carriers, which is sort of like quite special and really hard to understand. So why? So since we have a single point for a drug for encapsulate with high loading efficiency, we sort of try to understand why this happens and how we can try to further design and develop other drugs or even other trigger responsive systems for future applications to expand these systems. So how is the nanoparticle formed? The first idea we have is it micelle structure. As we know from a micelle, which is, because the polymer I use here is a polyethylene glycol co-block polylactide, which is an amphiphilic polymers, it will self-assemble into micelle when the concentration of this polymer is above the critical micelle concentration. So we assumed, so presumably this will form a micelle in the solution, and in general, the nanoprecipitation method drug should be encapsulated in the hydrophobic core of all these systems. However, for my system, it seems to be a little bit different from micelles. Several factors I listed here is that first, the drug loading should be limited by the hydrophobic core size, which should be less than 20% or 30%. However, for my system, the drug loading is more, you can reach as high as around 90%, which means that the majority of the particle is not the PAC-PLA. The second factor we need to consider is the particle size. I didn't show this data in the previous slides, but the micelle of the PAC-PLA I use, the size is around 30 to 40 nanometers in size. But the particle I made from my drugs is more than 100 nanometers, which is completely different. So it seems that the model used to explain the micelle nanoparticles is not suitable for my system, because for micelle drugs fill the hydrophobic core, but seems it's different from my systems. So why? So further evidence, I have done a little bit more experiment to try to confirm that it's not a micelle structures. The first very critical factors is that under critical micelle concentrations, the PAC-PLA micelle should be disassembled and not stable at room temperature for over 24 hours. However, for my system, I show you all the numbers here. For my particles, it's very stable even at very low concentrations, which is around actually less than 40-fold lower concentration of the carrier polymers, which indicated that my nanoparticle is not stabilized by the micelle interaction between the carrier polymers. So how is it stabilized? As we go deeper to see the structure of polyethylene glycol coblock polylactide, we can change the stereochemistry of this block of the polylactide, change it into a stereoregular structure or an irregular structures to make a difference. And very interesting, when we found that when we change our nanoparticles from irregular coblock polymer to a stereoregular polymers, the particle is less stable. So what does this mean? So actually for stereoregular polyalactide, the amphiphilic polymer micelle is more stable than the stereoirregular lactide, because the interaction between the lactide block is stronger. The interaction is stronger for the first polymer actually. So this means that my nanoparticles are not simply stabilized by PLA interaction. Instead, the drug-PL interaction and drug-drug interaction is more important in my systems, and they may be the driving force to stabilize my particles. So since we can compare with 3 possible states of my drugs within the nanoparticles. First is the micelles. The drugs distributed in the hydrophobic core of the micelle, and the size of the particle should be relatively small. And also another possibility is that drug is sort of like in a free state in water. So I want to tell you that the nanoparticle concentration I use is way higher than the drug solubility in water actually. So this is not the actual case, for sure not the case for my particles. Another possibility is that the drug itself forms a very compactly packed nanocrystals, or we call it nanoaggregates, and the packed PLA simply cover the surface to make it stable. So we sort of had some experiment to confirm this idea. So for my drug conjugates, I have a very special phenomenon called aggregation-quenching. The fluorescence of cathode is quenched in my drug conjugates in its aggregated state, while in its free form, for example, in organic solvent, the fluorescence is quite relatively strong. So we first do the lab experiment. We first dissolve my drug conjugates in water with the help of organic solvent at very low concentration, which should be a sort of like an aggregated state because it's mainly a water environment. So the fluorescence is quenched at first, and then we add excessive amount of polymer carrier. P55 is just a polymer I use, is the same as previously. So very interesting, after sonification, we can see that the fluorescence is sort of recovered. And finally, even only after 15 minutes ultrasonification, the fluorescence almost recovered to the same as that in my cells, indicating that in my cells, the drug is sort of like in its free form instead of an aggregated form. So when we do this experiment similarly, in our nanoparticle solutions, we can see that the particle is very stable, and it's always in its aggregated state within the core. Even after slightly sonification, the fluorescence doesn't change at all, indicating that the drug aggregation or the drug interaction is sort of strong. So let's come back to this question, how the particles are formed. So here's the process. I showed you this figure before, so it's just a scheme for micelle formation of nanoparticles. So here is our hypothesis, how is our explanation for it. During the nanoprecipitation process, since the drug solubility in water is quite low, so once the water diffuses into the droplet of DMF, the drug should precipitate and form sort of like an aggregate state from very tiny small crystals, and gradually it grows larger and larger. And during the process, since it has sort of some part of packed PLA in the solution, the packed PLA should diffuse onto the surface of these nanocrystals. And to a certain extent, the packed coverage reach a certain density which inhibit the further interaction between the inner core and the free drug that tend to precipitate out, which made the particle relatively stable. So from the process seems, from our explanation, it's sort of like a kinetic-driven process. So here's an actual experiment we try to confirm the mechanism we proposed. So for the nanopresentation, we dissolve all the components together in DMF and add it into water. So in this experiment, we first dissolve our polymer in water, then add the DMF solution of our drugs into the polymer aqueous solution to see what will happen. Actually, before any drugs, when we only dissolve the polymers, we can clearly see a micelle structure, and the size of this micelle is around 40 nanometer in size. And once we add a little bit drugs, only like less than 10% of drug compared to the micelles, actually the nanostructure clearly can be tuned by the drug addition. Actually, we can see that the size of the nanostructure within the solution grows up to around 118 nanometer in size. And further addition of the drugs doesn't change these nanostructures at all. So we can imagine if it's really a micelle structure or the other kind of structure that the drugs gradually fill into the hydrophobic core. After we add our drugs more and more into water, the hydrophobic core should grow larger and larger. So the size should not be maintained. Instead, it should grow higher instead of suddenly jump at the first drop of drugs is added. So this further indicated that when the drug is into solution, it forms an aggregate, and so the micelle disassemble in solution and cover the surface of the nanoparticles. So here is sort of like summarize the idea I have. So why it works for my drugs, conjugates, and why it doesn't work for the camptothecin itself. Our explanation for this is that for the drugs, because of its sort of like very special structures in it, the self-aggregation of the drug is relatively slow. While for camptothecin itself, the aggregation is too fast, such that in the process, the PAC-PLA carriers doesn't have enough time to migrate onto the surface of the aggregate, so that we only see very micron-sized or even larger aggregates for the camptothecin. While for my particles, since the aggregation process is relatively slow and also comparable to the migration of PAC-PLA, the particles can be formed in a relatively stable state, and the size seems to be very lucky to drop into less than 200 nanometer, which is suitable for in vivo applications. So here is a further simple evidence we have for that kinetic-driven process we explained. So when we simply change the mixing rate, when we do this nanoprecipitation, we can see the higher the rate, the smaller the particle size. Because we can imagine when we mixing it better, the migration of PAC-PLAs should be better faster onto the crystal surface, so that the particle size should be smaller. And when we use a non-mixing strategy, use dialysis, the particle size is way higher than that when we do with nanoprecipitations. So with all that, we sort of have approximate idea about how it's formed. So I will show you next for some future applications for it. As I told you that we want to make all these particles for cancer therapies and for trigger-responsive drug deliveries. So I first confirmed the trigger-responsive property of my drugs. Actually, we can see a very clear trend when we don't add any triggers into the nanoparticle solutions, none of the drug is released. While when we put a certain amount of cell triggers into the solution, the cell-responsive nanoparticles show a very clear trend to release only the free camptothecin in the solution. Instead, we don't see any we don't even see any original drug release leakage from the nanoparticles. And a very brief demonstration for in vivo efficacy, we do an MTT assay to evaluate cytotoxicity to compare camptothecin with our nanoparticles, as well as irinotecan, which is a derivative of camptothecin and is clinically widely used for colon cancer treatment. And we can see, because camptothecin for sure cannot be used for in vivo delivery, so the toxicity is a little bit higher than our particles, but our particles seems to be better than irinotecan itself, because irinotecan takes some time to metabolize to a certain active species, while our nanoparticles can only release a camptothecin, can be responsive to intracellular cell levels. I have a very brief demonstration of in vivo efficacy for these systems. We use 41 murine breast cancer tumor models with xenograft tumors on mice. And through intravenous injection of my nanoparticles, we analyze the tumor sections to see about apoptotic level of the tumor cells within all these two cancer tissues. And we compare it with both negative control PBS, positive control irinotecan, and our nanoparticles. We can see a clearly trend that our nanoparticles greatly increase the apoptotic cell percentage in the process. And even within 3 days, we can see around more than 30% of the cells are undergoing apoptotic process, which suggested that our particle has really good potential for further in vivo or further translational applications. So that's pretty much my work I want to talk about today. So to summarize it, I have shown you one of the drugs, one of the cathode conjugate we discovered, which has very high drug loadings. For the benefit of our system is listed here, as we have our drug conjugate mixed with polymer carriers. It's two-component formulation. We can well control composition because we have quantitative drug loadings in it, and we have a defined drug loading as long as you feed it with controlled ratio between these drugs and the polymers. And since we have two components in it, we can further modify the simple polymer structures to make it surface with either aptamer or some other ligand for targeting cancer targeting. And we can control the release through the certain original design of our systems. Future directions for this study will be a computational simulation to more understand all these processes and why it happens, but I'm still trying to looking for collaborators for that. And more like nanomedicine-wise, we try to focus on how to control the shape of nanoparticles and size, how to control size of nanoparticles, as well as service modification for further cancer targeting studies. So with that, I would like to thank all my advisors, Professor Chen for a lot of suggestions in the process, Professor Helfrich and Dob Rookies in the process, and all the Chen group members for the help. And thanks for your attention, and I would like to answer any questions you have.